participate. I comprehend that you are the James Webb Telescope's primary scientist and that it's about to launch. Also, who exactly are you? I hope that helps you understand the commencement, subsequent research, and the information returned to us. And what I really want is for us to receive a big surprise from our new observatory because that has always happened. Every time we built a new great observatory, something no one had ever guessed was out there appeared. Thus, it serves as a reminder that our imagination, regardless of how agitated we might feel, is still limited, and we don't usually predict what nature has done. Imagine yourself lurching along in an endless sea of shadows. The Milky Way, our galaxy, is all around you, a brilliant, whirling city of light. We've been at it for more than a century, holding a core belief about our universe that, on the most grand scale, it's basically the same everywhere. That is a pillar of the cosmological principle in current science. But what happens if that pillar breaks? What if our cosmic address isn't in a bustling, typical neighborhood but out in the expansive, tranquil countryside? Sounds like science fiction, doesn't it? Well, it might actually be closer to the truth of our existence than we think. An idea that was once outside the mainstream of astronomy is currently gaining serious reconsideration. This is all due to the most powerful space telescope ever made. Not that the James Webb Space Telescope has delivered a final verdict, but its strong eyes are offering enticing new information regarding one of the most unsettling ideas in science, the possibility that we are living inside a cosmic void. Why does this matter? To grasp how revolutionary the idea of living in a void is, you must first comprehend the picture it attempts to replace. The lighthouse for cosmologists has long been the cosmological principle. The gist of it is that the universe is uniform and isotropic on the largest scales. That is to say, no matter where you look, it should be essentially the same. There's no center, no edge, no special spots. Imagine yourself in a massive forest. You can see it all around you. Individual trees, spaces between them, and dense patches. However, from an airplane, the entire forest simply resembles a uniform carpet of green. The cosmological principle assumes that the universe is similar to that carpet. Our local cluster of galaxies is merely a small group of trees, but when averaged across billions of light years, everything smooths out? This was more than just a guess. The most persuasive evidence came from the CMB, the cosmic microwave background. This is the faint leftover heat from the Big Bang. It's everywhere. When we mapped the CMB, it was remarkably uniform. This smoothness was interpreted as evidence that the early universe was incredibly even, forming the bedrock of our standard cosmological model, lambda-CDM. This model has been a huge success, describing nearly everything, from how the universe expands to how galaxies form. It tells a tale in which denser regions of a primordial soup gradually absorbed more matter, constructing the vast cosmic web we see today. Glittering filaments of galaxies connecting huge groups with voids in between. These voids were predicted by the standard model, but it always assumed we lived on one of the filaments, a typical part of the cosmic web. For decades, that was our cosmic address. However, astronomers began noticing things that did not make sense. The first hints that our cosmic neighborhood might be unusual appeared decades ago. In the 1970s and 80s, astronomers began mapping the 3D positions of galaxies and discovered something unexpected. The cosmos was not smooth at all. It was packed with galaxies arranged in huge walls and filaments, which surrounded enormous, almost empty regions. The most famous of these was discovered in 1981, the Boat's Void. This was no ordinary gap. It was a baffling 330 million light-years across, a region so devoid of galaxies that, if we were in the middle of it, we might have no idea that other galaxies existed. Its scale seemed to defy conventional models. As maps improved, more voids were discovered. They are like the air pockets in a cosmic sponge, occupying the majority of the universe by volume. Still, the assumption was that we lived on the sponge, not in the holes. That is, until a more direct challenge arose from a group of astronomers, including Amy Barger. They analyzed data from multiple sky surveys and found that our region of the universe appeared to have significantly fewer galaxies than average. They suggested that we weren't just near a void, we were inside a massive one, approximately 2 billion light-years across. They called it the KBC void. This was a radical idea. It hinted that our location is unique and that our perception of the universe might be skewed. For many, this felt like a return to the old notion that we are at a special spot in the universe. Yet the void hypothesis offered an elegant solution to an even bigger problem brewing in cosmology, the Hubble tension. That's the enduring disagreement over a single number, the speed at which the universe is expanding. The issue is that we have to principle methods, and they provide us with two different answers. The first approach looks deeply into the past, using the cosmic microwave background and the standard model to predict today's expansion rate, about 67 kilometers per second per megaparsec. The second approach measures the local expansion rate by observing standard candles, Cepheid stars, and supernovae to calculate distances to nearby galaxies. And the results. Fast, they're moving away from us. This method always delivers a higher number, around 73. The discrepancy between 67 and 73 is not an accident. The dimensions are now measured with such accuracy that their error bars do not overlap. There are three possible meanings. Our understanding of the early universe is wrong, our local measurements are incorrect, or the model that links them together is faulty. The void is located here. The hypothesis returns, suppose we reside inside a huge, dense bubble. The theory suggests that the denser regions surrounding this void would have a greater force of attraction. Galaxies, including us, would be pulled into the void toward the denser edges. This local movement would add to the cosmic expansion as a whole, making it appear that the local universe is growing at a rate faster than the global average. It suggests the Hubble tension is a local problem, not a crisis at all. Our universe's speedometer is reading high because we are taking measurements within a valley. But how could you ever prove you're trapped within a forest? You'd need a new set of eyes, something powerful enough to map the entire terrain. That's where James Webb Space Telescope comes in. Webb is a machine designed to display the universe in a completely new light, ultraviolet and infrared. As the universe expands, it stretches light from far away into the infrared spectrum of galaxies. The huge golden mirror on Webb is designed to capture this ancient, dim light, enabling it to produce the largest and deepest cosmic maps ever attempted. This is precisely what needs to be tested, the concept of voids. To find out if we are in an area of lower density, you'd need an accurate galaxy census. Webb has now pointed its mirror at the sky and declared, "Case closed, we live in a void." No, not yet. However, what it's doing is providing the most pristine, high-definition data to test this idea. COSMOS Webb, a massive undertaking, is dedicating hundreds of hours to mapping an enormous area of sky registering as many as 1 million galaxies. The early images are shocking, revealing the cosmic web in incredible depth, bright filaments of galaxies separated by vast dark expanses. These diagrams will allow scientists to compare our local galaxy density with the cosmic average at an unprecedented level of precision. At the same time, Webb is also refining the Hubble tension itself. A few hoped the issue was merely caused by errors in our local measurements, but Webb's new observations of Cepheid stars are so accurate that they have confirmed the 73 value, lowering the probability that it's all simply a calibration error. In a sense, Webb has increased the pressure to find a physical justification. It has made the void hypothesis a more necessary and compelling line of inquiry. So, let's think about it for a moment. What if the evidence continues to build, and it turns out we do live in a giant cosmic void? What would that actually mean? The Hubble tensio. The cosmological principle that we live in an average place would be shown to be an oversimplification. And beyond the numbers, this would carry profound philosophical implications. Science has always moved us further from the center of things. But the void hypothesis brings back a strange kind of uniqueness. We would not be at the center, but we would occupy a one-of-a-kind, empty, quiet location. Could this explain why we are here? Is it really just us, or is our isolation a symptom of a larger cosmic purpose? In denser, more typical regions of space, destructive events like galactic mergers or nearby supernovae are more common. Perhaps our quiet corner of the universe has provided a safe harbor, a secure nursery where life could flourish across billions of years. Our cosmic isolation may be the very reason we're here to think about it. It's a humbling thought, one that forces us to reevaluate our perspective. It reminds us that we are looking out over the universe not from a mountain peak, but from a valley floor. James Webb hasn't closed the book on this mystery. If anything, it has opened the doors wider. It is providing us with the sharpest tools ever built, and its initial findings are only deepening the intrigue. The data support the fundamental filament-tanned void structure of the universe with incredible clarity, while at the same time reinforcing the very tension a local void could resolve. The final confirmation, however, is still on the horizon. Webb is sending terabytes of data home as scientists carefully construct a comprehensive census of our cosmic neighborhood, searching for statistical evidence of a deficit and for signs that galaxies are drifting away from us. This is real science at work, a cosmic investigation on the largest scale imaginable. So, are we adrift in a great cosmic nothingness? Is our isolation the key to our very existence? These are the final pages, yet there are still mysteries to be written. As Webb's golden eye keeps looking deeper into the cosmos, we await evidence that could definitively redefine our place in the universe. What are your thoughts? Could living in an empty region of space really explain the Hubble tension? Or is something even stranger going on? Please share your thoughts in the comments. And if you want to stay on the cutting edge of these cosmic discoveries, subscribe so we can float through the void together. In the meantime, keep looking up.